Hello dear students. In the previous session, we have discussed what social network analysis is and explored different types of social media. So today, in this session, we are going to learn the foundation of social network analysis, namely graph essentials. Every social network, transportation system, communication network, and even biological system can be represented using graphs. Once we understand graphs, we can analyze complex real-world problems much more easily. So the core subject is at the end of this session, we should be able to understand what a graph is, differentiate between graphs and networks, identify nodes and edges, calculate the degree of nodes, understand degree distribution. So the next one is bridges of Königsberg problem. So let us start with a famous puzzle. Imagine there are two islands connected to the mainland by 7 bridges. The challenge is, can you walk through the city by crossing every bridge exactly once? Before computers existed, this puzzle fascinated mathematicians. Can anyone guess whether it is possible? Yes, this simple puzzle actually led to the birth of graph theory, which is now used in Google Maps, Facebook, AI, and many other applications. So, instead of looking at the actual city map, Euler simplified the problem. He represented land areas as nodes, it means vertices, and bridges as edges. This transformed a complicated map into a simple graph. This teaches us an important lesson. Many difficult real-world problems become easier when represented as graphs. So and then Euler's solution. So whenever we enter a location through one bridge, we must leave through another bridge. Therefore, except for the starting and ending points, every location should have an even number of connected bridges. However, in this graph, several locations have an odd number of bridges. Hence, it is impossible to cross each bridge exactly once. This result is known as Euler path theorem. So now let's move from graphs to networks. A network is simply a graph where every node and edge has a real world meaning. For example, Twitter users or nodes, follow relationships or edges. Suppose one user posts important information. How can we spread it to every connected user with minimum cost? That becomes a network optimization problem. So in the network graph theory versus network theory, students often confuse graph theory and network theory. Graph theory mainly studies mathematical structures. Network theory studies practical systems where nodes and edges represent real objects. Examples, graph theories are Euler path, Hamiltonian cycle, and for examples for network theory, Facebook, internet, road networks, and communication systems. So think of graph theory as mathematics and network theory as engineering. So and then networks are everywhere. Networks are present almost everywhere. It means an internet, food chain, citation networks, Twitter, brain networks, airline routes. So and the internet is one of the world's largest network. Here routers or nodes, communication links or edges. When you open a website, your data travels through many intermediate routers before reaching the destination. So in the highway network, road system can also be represented using graphs. Cities become nodes, roads roads become edges. Google Maps uses graph algorithms to calculate the shortest route between two places. Ask which algorithm have you studied for shortest cut? So what is that? The expected answer is an Dijkstra, which we already studied in the data structures concept. So the next one is social networks. Social network is a network where the nodes are people or organizations. Examples: family, friends, office colleagues, LinkedIn connections. These relationships help us understand, influence, communication, and information flow. So the next one is high school friendship network. This figure shows friendship among students. Each circle represents a student. Each connecting line represents friendship. Notice that students naturally form groups. So this graph represents dating relationship among students. Unlike friendship, these relationships create interesting patterns. So researchers analyze such graphs to understand human behavior, social influence, and information spread. So the next concept is graph basics. Now we come to the most important topic, a graph, which consists of nodes, vertices, edges called as links. This is the building block of social network analysis. Everything we study later depends on these two components. So nodes and edges. A node represents an object. Examples: Facebook user, LinkedIn professional, road network city, and for airport network airport. Edges represent relationship between these nodes. So examples: friendship road, flight communication. So the circle represents the node or vertices and the line represents the edges. So nodes are actors. In social network analysis, nodes are often called actors. Depending on the application, a node could represent person, company, website, computer, mobile phone, and country. The meaning changes depending on the problem. So the next one is edges. So edges represent relationship. Example: friendship, following, email communication, business partnership. Without edges, the graph contains isolated nodes and no interaction. So edge can be represented at the set E1, E2 up to m number of edges. So the next one is directed graph. Sometimes relationships have direction. Example: Twitter. If I follow Elon Musk, it does not mean Elon Musk follows me. So the edge has a direction. These are called directed graphs. Draw an arrow on the board to explain the edge. So directed versus undirected. Facebook friendship is usually undirected because both users agree to become friends. Twitter follow is directed because only one person follows another. Always ask, is the relationship mutual? If yes, undirected. If no, directed. So the next one is neighborhood and degree. So the neighborhood of a node means all nodes directly connected to it. Suppose a student has 5 friends, then neighborhood equal to those 5 friends. So that degree equal to 5. Degree tells us how well connected a node is. So